Today I'd like to tell you about time, more precisely about measuring time. Measuring time and building clocks has been a human endeavor for millennia. Measuring time is a practical, technological, and commercial need. And for that, people build clocks. What are clocks? Clocks are physical systems that are periodic. They do something again and again and again and again. If you want to know how much time passed, you measure how much periods of the clock have gone by, and therefore you know the time. Probably the most ancient clock we're familiar with is the sundial. People have been building these sundials for centuries. A sundial relies on a periodic phenomena, which is the rotation of Earth around itself. When Earth rotates around itself, the position of the sun in the sky changes, and therefore the shadow that the pole in the center of the sundial changes across the clock. Earth rotates around itself again and again and again, and therefore you know how much time passed. It's a very simple clock, it's a very basic clock, it's very easy to build, but it's not very precise. It's not very precise because the rotation frequency of Earth around itself is not stable. It drifts. An even worse problem is it's a very slow clock. If you want to know how much time passed in a time range of minutes or seconds, the shadow on a sundial would not change by much, and therefore it's not a very practical clock if you want to look at very short time intervals. And therefore, throughout the centuries, people looked for periodic phenomena that are faster. Here is another example, the pendulum clock. The pendulum clock relies on the periods of a swing. You hang a heavy mass at the end of a rigid rod. You have a small spring that pushes the rod back and forth, and therefore you get a periodic phenomena, the oscillations of the swing. This is again a very simple clock to build. It can be very compact. You don't need the sun to be in the sky for it to operate. It can operate at night. It also has some disadvantages. For example, the frequency is also not necessarily very stable. It depends, for example, on the length of the rod. If you compare two such clocks with rods that have slightly different lengths, they would oscillate at different frequencies. Even worse, if the temperature, the humidity, other conditions vary, the length of the rod would vary as well, and the frequency of the clock would drift. Building clocks is a technological challenge that is intimately related to another technological challenge, which is that of navigation. In the 16th and the 17th and the 18th century, when the naval powers have sent ships to cross the ocean, sailors had to navigate across the ocean and far away from shorelines that gave them good indications as for where they were. So if you want to know where you are in the middle of the ocean, you need to be able to determine two coordinates, your longitude and your latitude. Determining your latitude is a relatively easy task. All you have to ask yourself is, where is the sun at midday? If the sun is right above your head at midday, that means you're right on the equator. If at midday the sun is south of you, that means you're north of the equator, and vice versa. Measuring the longitude is a much more difficult task, because if you ask yourself, where is the sun at midday, it's right above your head, or slightly south, or slightly north. East-west is not going to give you any information. If you want to know, all you need is a precise clock that will tell you it's noon at your port of departure. If it's noon at your port of departure and the sun is west of you, that means you're east of that port, and vice versa. So you need a clock that would maintain its accuracy over a long voyage in sea. For those of you who are number savvy, let's go through a simple exercise to determine how accurate that clock needs to be. If the circumference of Earth along the equator is 40,000 kilometers, and you would like to know where you are with an accuracy of 40 kilometers, that means you need to be able to determine time with an accuracy of 24 hours, the period of Earth rotating around itself, divided by 1,000, which translates to about a minute and a half. So the challenge that the naval empires faced 200 years ago was to find a clock that is sufficiently accurate to maintain an accuracy of about a minute and a half over a journey of half a year or a year and a half across the seas. This was a sufficiently important challenge that the naval empires have offered a monetary award, which is equivalent to about $10 million in today's currency, for the genius that would solve the longitude problem. The best brains on Earth at that time have embarked on that intellectual journey. Galileo Galilei thought that with his newly invented telescope, he could look at the moons of Jupiter that would serve as dials on this astronomical clock. And because of that invention, the Medicis of Florence, his lords, were able to sign a strategic treaty with the naval empire of Spain at that time. That clock proved to be not very useful in long journeys. The gentleman who, at the end, actually solved the longitudinal problem is this handsome gentleman here, John Harrison of England, who was a genius engineer. He was not a scientist at all. In fact, he grew up as a church tower clock builder. He came up with many ingenious ideas and inventions, such as the bimetal spring that uses the opposite thermal expansion coefficient of two metals in order to construct a spring that would not change its length as the temperature varies. And by using all these tricks, John Harrison was able to build clocks that were sufficiently accurate in order for ships that cross the sea to determine their accuracy with sufficient resolution, leading in fact to British dominance over the seas for the next 2 centuries. Precision clocks are still intimately related to navigation. Today, all of us navigate using the global positioning system, and the global positioning system uses atomic clocks, very precise clocks on board of satellites, and triangulation of the signals that come from these satellites to Earth. The way GPS works is that all these satellites, using their clocks on board, send timestamps, time signals. We receive these time signals in our GPS device, let's say our cell phone. We compare the time reading that we receive to the actual time on our clock. And therefore, we know the time it took the signal to travel from the satellite to our device. If we divide that time interval by the speed of light, we know the distance of that satellite from us. For those of you who are geometry savvy, if we know the distance from us to the satellite, we know our position up to a sphere which is centered around that satellite. If we repeat that exercise with another satellite, having 2 such signals, we know our position up to the intersection of 2 spheres, which is a ring. If we repeat that exercise with 3 satellites, hence triangulation, we know our position on the intersection of 3 spheres, hence on a point, and therefore we know exactly where we are. Again, in order for GPS to work, we need precise clocks on board of satellites. The clocks on board satellites are atomic clocks. What you see here is an example of an atomic clock in our lab at the Weizmann Institute of Science. What you see here is a vacuum chamber with a trap inside. That trap hosts atoms. Atoms, naively speaking, are like small solar systems with electron encircling the nucleus of the atoms. Atoms are not really planets. They're very small. They're quantum systems. And therefore, electrons in atoms don't have a clear linear trajectory. In fact, electrons in atoms are these fuzzy clouds of probability around the nucleus. Nevertheless, they're very precise, very stable periodic systems, and therefore can serve as excellent clocks. Since they're quantum systems, quantum mechanics also imposes limits to the accuracy of the clock. One of these limits is, in fact, the Heisenberg uncertainty principle. Another limit that quantum mechanics imposes on the accuracy of these clocks is due to the fact that in quantum mechanics, when you measure a system, its wave function collapses. When we measure the electron, we actually perturb the operation of the clock. And therefore, when we want to know time with great accuracy, we need to repeat the measurement of the atoms over and over again, or over a large ensemble of atoms. Nevertheless, these atomic clocks are the best clocks we have today. Atomic clocks on board GPS satellites can find time with an accuracy of 10 to the 12. In other words, they have the accuracy of 1 picosecond over a second, and that's sufficient for GPS to work with the accuracy it works today. The best atomic clocks today are optical atomic clocks, and they're 1 million times more accurate. In our lab at the Weizmann Institute of Science, we build optical atomic clocks using trapped ions. Ions are atoms that are lacking one electron. They still have a sufficient number of electrons in order to perform as good clocks. We keep these atoms, these ions, in ultra-high vacuum, and we cool them using laser cooling techniques to a millionth of a degree above absolute zero, where their behavior is very, very quantum mechanical. One main difference between regular atomic clocks, similar to those on board satellites, and optical atomic clocks is that regular atomic clocks uses microwave radiation, similar to the radiation that you use in your microwave oven or in your cell phone in order to communicate between phones. This is radiation that oscillates a few billion times per second. Optical atomic clocks also use electromagnetic radiation, but they use electromagnetic radiation which is 1,000,000 times faster. It oscillates at 10 to the 15 times a second. In other words, we're using laser light in order to operate our clocks. Our clocks are sufficiently accurate in order to measure the effects of relativity in our lab. Einstein has told us that there is no such thing as a universal time, and there is no such thing as universal space. Both time and space are relative notion. There is no big clock which is operating in the background of the universe, and there is no ruler with which we can measure distances and all agree on what distance is between 2 points. Both these are relative notions. In fact, when two observers would look at two events, one of them would claim that these two events have happened simultaneously, and the other would claim that they did not. It's not necessarily that one of them is wrong. They could both be right because time is a relative notion and depends on the frame of reference. One result of time being a relative notion is the following fact. If you place two clocks, one at a higher gravitational potential and one at a lower gravitational potential, the clock at the higher gravitational potential would tick slower. In fact, if you would place a clock on the horizon of a black hole, time would come to a complete standstill. There will be no events at all on the horizon of a black hole. So, when you place clocks on a GPS satellite, you have to take into account the fact that this clock is much farther away from Earth and therefore ticks faster as compared to clocks on Earth. If you take our optical atomic clocks, they're sufficiently accurate to measure gravitational slowing down of time, even on heights that are as small as the size of a person. If you'll place one of them close to the person's head and one of them close to the person's feet, you'll see the one close to the person's head ticking faster, which means that tall people do think faster. Here's another example for a relativistic effect that our clocks are sufficiently accurate to measure. In relativity theory, if you'll take two twins, one of them would stay on Earth, the other one would hop into a spaceship and would fly to the next solar system and return in a couple of hours, you'll find out that his twin is already an elderly person with grandchildren and close to the end of his life. And the reason for that is that in relativity, if you travel faster and you accelerate to high speeds, time goes by slower. The twin on Earth would feel time going by much faster. This effect is very, very important if you travel at speeds close to the speed of light. Our clocks are sufficiently accurate to measure this twin paradox even at velocities that are the velocities of human running speed. Therefore, in other words, our clocks are sufficiently accurate to measure relativistic effects under normal lab Earth conditions, which is really mind-blowing. What you see here is a picture of our optical atomic clock in our lab. As you can see, it's a pretty compact, small device. It could probably fit into your dinner table. It's the size of a TV set, perhaps. What you see here is a vacuum chamber and a camera that detects the light which is being emitted from our ions. You can see optical fibers streaming laser light into the experiment. So, as I said, we work very hard in order to build precise clocks. Why do we even need precise clocks? Well, I think one reason to build precise, better and better clocks, more and more precise clocks, is because we can. Like any other human endeavor, if you can improve yourself, you'll try to improve yourself. It's a race between different groups in different universities. But there are also practical reasons in order for us to improve our timekeeping devices. One example, we already discussed, the global positioning system. If we would like navigation systems to perform better, we need better clocks. If we would like to navigate farther out, we would like to navigate into deep space, we need better clocks. We all use high bandwidth communication networks. If we want our communication networks to sync in at a very high rate, we need better clocks. We need better clocks in order to have better cybersecurity in banking. In science, if we want to measure things accurately, we better translate that measurement into frequency and then measure that frequency. The accuracy of any lab is ultimately limited by the precision of the lab clock. Here's another example which I particularly like, and that is our clocks are sufficiently accurate in order to detect new matter, new particles, new forces, new fields. How would we do that? Here's one example. Most scientists today would agree that 80% of the universe is composed out of matter that we're unfamiliar with. We call it dark matter. We call it dark matter because it does not emit light. We don't see it. It interacts very weakly with normal matter. We actually assume that tons of dark matter flow through us, through Earth, through our houses, through our bodies, and we don't know it. The reason we don't know it is because we're completely transparent to this dark matter. The atoms in our body only very weakly interact with these dark matter particles. However, even if the atoms interact very weakly with dark matter, our clocks, atomic clocks, are so sensitive to perturbations in the electron trajectory around the nucleus that even with a small, very weak interaction between dark matter particles and our clocks, they'll perturb our clock operation in a way that we will be able to detect. So at our lab at the Weizmann Institute, we use our optical atomic clocks in order to try and detect new particles. Most experiments that are trying to detect new particles are done in large colliders. What you see here is a picture of the Large Hadron Collider in CERN in Geneva. It's a very big machine. It accelerates particles to extremely high energies, and these particles collide at high energies, and the collider searches for new particles that would be emitted from the collision. As I said, it's a big device. The LHC is 27 kilometers in circumference and buried 175 meters underground. It's the result of the hard work of thousands and thousands of scientists over a couple of decades. We search for new particles using optical atomic clocks. As I said, much more compact devices, very sensitive. They work in the low energy regime. We cool our ions to extremely low temperatures. It runs at labs, small labs, at a small research institute such as the Weizmann Institute of Science, and they're constructed by a relatively small group of students and researchers. So to conclude, why do we need precise clocks? The reason we need precise clocks is because the increasing pace of modern life demands better and better timekeeping devices. In our lab, we use quantum systems. We use the laws of quantum physics to enable improvements and breakthroughs in timekeeping. So, to conclude, I'd like to thank you for your time.